Deep in the Madagascar rainforest, Darwin's bark spider spins webs on a staggering scale. It releases a single thread into the wind, letting it drift until it anchors to the opposite bank, bridging rivers up to 25 meters wide. To hold massive webs suspended over open water, that anchor thread, known as dragline silk, absorbs more than 10 times as much energy as Kevlar before it snaps. It is the toughest biological material ever measured. This chart shows the specific mechanics of toughness. Unlike simple strength, which is just the load a fiber can bear before breaking, toughness accounts for both strength and extensibility, or how far it can stretch. The total area underneath this curve represents the energy the silk can soak up before it fails. But acquiring enough of this material for testing requires a monumental effort. When Adam Savage and his team at Mythbusters Jr. tested the tensile strength of spider silk, they spent 2 months extracting 10 miles of thread from 40 golden silk orb weavers just to braid a single 2-foot-long rope. We have discovered a natural fiber that outperforms our best engineering labs, yet extracting it from its biological source cannot be scaled up for mass production. We have harvested wool from sheep for millennia and commercial silk from silkworms for over 5,000 years. The logical next step would seem to be building commercial farms for spiders. Spiders, however, are highly territorial apex predators. They do not behave like docile livestock. If you place thousands of them into a confined manufacturing facility, they will cannibalize one another until only a single spider is left. Because the animal's biology prevents industrial harvesting, we cannot rely on the spider itself. To produce this silk at scale, researchers have to separate the material from the organism. To bypass the spider, researchers zoomed in on its biology at the molecular level, searching for the exact genetic sequences responsible for spinning the silk. Scientists isolated spidrins, the proteins giving spider silk its properties, and mapped the code telling the spider's glands how to build them. Using recombinant technology, researchers inserted this blueprint into the DNA of a more cooperative host organism. By inserting these genes into microbes or yeast, biotech startups can now ferment spider silk polymers inside industrial vats, producing the raw material without a single insect involved. By translating the spider's protein instructions into a laboratory setting, scientists have turned a natural resource into a programmable output. But humanity already possesses a massive agricultural infrastructure designed for a single purpose: harvesting thread from the domesticated silkworm, refined over 5,000 years. Researchers at Craig Biocraft Laboratories decided to utilize that existing infrastructure by inserting the spider's spiderwing genes directly into the embryos of these domesticated silkworms. Inside the transgenic silkworm's glands, engineered spider silk proteins are produced alongside native proteins, blending into a single cohesive fiber as the worm spins. The result is dragon silk. The docile worm spins a harvestable cocoon that yields a hybrid fiber with the mechanical strength of the spider's DNA. By reprogramming an insect we domesticated in antiquity, we created a living factory for a high-performance material. Production has moved past extracting milligrams in a laboratory. Companies are now ramping up facilities to produce metric tons of synthetic spider silk for commercial supply chains. One of the immediate applications is in defense. Dragon silk is being developed for ultra-lightweight body armor that can absorb high-velocity impacts while remaining flexible. In consumer markets, startups like Inspider and Bolt Threads are formulating these silk biopolymers into sustainable leather alternatives and textiles, replacing traditional petroleum-based fabrics and animal hides. The medical industry is leveraging the material's high biocompatibility. Surgeons are exploring synthetic spider silk as a structural matrix to engineer artificial blood vessels and reconstruct torn ligaments in the knee. Israeli startup Cevix is formulating artificial spider silk that retains the self-healing properties of a natural web, integrating it into surgical sutures designed to help wounds repair with less scarring. By isolating and replicating the spider's protein instructions, we have established a method for mass-producing high-performance materials through biological manufacturing.